Hello, Dr. Jorgensen and fellow proof students. My name is Ryan Schulze, and today I am going to be doing my oral presentation on fact number 1 in section 1.5 recursive definitions. What is fact number 1? Fact number 1 is the following, that there is a set A, and A is defined by this linear combination, m1, n1 plus m2, n2, where m1 and n2 are the elements of z, so all of the integers. And n1 and n2 are fixed natural numbers. In this very set, we're going to assume that there is some g that is the smallest natural number in A. It's the smallest thing this linear combination can produce. And we're trying to prove that g is equal to the GCD of the two fixed natural numbers. In order to determine and prove this proof, we're going to be breaking it up into 3 parts, and we're going to be sequentially proving each part after the other in order to prove the entirety of this proof. The very first part of this proof is going to utilize the division algorithm. And the very first thing is to identify what g is. We've already done that. It's the smallest natural number in A. Now, we know that the division algorithm follows this form. That sum z is equal to sum q times sum d plus some remainder r. We're going to be adjusting it for the sake of our circumstances in this proof. We're going to suppose, let there be some x, where x is equal to the very linear combination in A. So x is equal to m1, n2 plus m2, n2. It's equal to the very same linear combination there. Now, we are going to say, let there exist some q and some r such that x is equal to gq plus r. And we know by the division algorithm, r can't be any single number. R is bounded. R is less than or equal to 0, but must be less than g. So, what is g? We've already established that g is the smallest natural number in A. So that means g within itself is just another linear combination. So g is going to be equal to sum A, n1 plus b, n2. Or just like m1 and m2, a and b are just the elements of all the integers. And these will guarantee that we get the smallest value of the linear combination. Knowing that, we can rewrite the entire division algorithm in terms of r. So r is equal to x minus gq, and then we can further algebraically expand that to the following. Where r is equal to m1 n1 plus m2 n2 minus q quantity times a n1 plus b n2. And then we can, further expand that as such. Where we can get the quantities and multiply them. M1 minus AQ times N1 plus M2 minus BQ times N2. Now, what is the point of all this? All of this shows that R is an element within A, because all R is just adjustments to the linear combinations that we already know exist within A. It's just an adjustment of X and G. So, we can also, knowing the division algorithm, determine what is R equal to. We've already established that r is equal to and bounded as such. So it must be less than or equal to 0 or less than g. However, what did we establish that g already is? We've established that g, by definition, is the smallest natural number in A. So it cannot equal g. It must equal 0, because we've already chosen what the smallest natural number in A is. If we said it was anything bigger than g, it's contradictory. Therefore, it's 0. That means we can go back and rewrite the division algorithm. So that means x is equal to qg. What does that mean? That means x is just the multiple of g, and we already established that x is just this linear combination that exists within A. So that means that G times any Q value is going to give you some X. So X are just multiples of G. And that concludes what part 1 is. Moving on to part 2, we need to determine the following. That G divides N1, G divides N2, and that G is less than or equal to the GCD of N1 and N2. We need to prove that. And this is much simpler than part 1. Does N1 exist within A? The answer is yes. If you make this 1 and you make this 0, you're going to get just N1. And we've already established that G is the smallest element in here, so that means G divides N1. So does G divide N2? Yes, once again, you just make this 0 and you make this 1, and you only get N2 in there. And we established, once again, G is the smallest thing in here, so it has to divide that. So G divides N1 and N2 by simple fact that they just exist within A. Because these both exist within A and divisible by G, by the very definition, we know that G divides the GCD of N1 and N2. Just by the definition of GCD. In order for G to divide this, G has to be less than or equal to the GCD of N1 and N2. Because you can't have anything bigger divided out, otherwise it's not divisible, because you're going to have a larger integer dividing a smaller integer. So you're not going to get an integer, so it's not divisible as such. That concludes part 2. Part 3, once again, pretty simple. We need to prove the following. That the GCD of N1 and N2 divides N1, the GCD of N1 and N2 divides N2. Is this true? Does this happen? The answer is just yes. You get the GCD and you multiply it by some other integer, you get N1. The same thing with N2. So that means the GCD has to divide them out. What does that mean for G? We've already established that G is just a linear combination of N1 and N2. It's just an A times N1 plus a B times an N2. As such, by the definition of the GCD of N1 and N2 divides G. However, if you recall from part 2, we know that G divides the GCD of N1 and N2. The only way for this to happen forwards and backwards, you just determine to one conclusion. That means G must equal the GCD of N1 and N2. Because anything divided by itself is 1. So G divides the GCD, and the GCD divides G. So this proof has already established the definition of G, and that G is the GCD of N1 and N2. And as such, it's the smallest natural number in the set A. So we have, through 3 parts, determined and proved that G is the smallest element in A, and that it's equal to the GCD. And that concludes our proof. Thank you very much, Dr. Jorgensen. Have a good day.